Engineers design structures to withstand static loads, but the real threat to integrity comes from vibration. Dynamic, oscillating forces can quickly tear a suspension bridge or an airframe apart. Predicting this movement requires solving the classical equations of motion, but trying to do this in the time domain, tracking every microsecond of a mass's acceleration, velocity, and position, is mathematically brutal and inefficient. Tracking a single mass bouncing on a spring yields a displacement that traces out a messy, continuously varying sinusoidal wave. To bypass this calculus problem, engineers assume the shaking reaches a steady state and route the physics through the complex exponential. This specific mathematical operation replaces the fluctuating wave with a single constant algebraic term. As shown here, xn represents the complex amplitude of the system. This constant encodes two parameters simultaneously: the magnitude, representing maximum physical displacement, and the phase, which tracks the timing delay between the driving force and the structure's response. Translating oscillations into complex algebra freezes the motion, replacing a shifting timeline with a static geometric map. This transformation makes the forces acting on the structure readable at any single point in time. Visualizing the complex exponential requires moving from a linear timeline to a rotating compass. The exponential term takes that chaotic up and down wiggling and transforms it into a smooth, constant circular rotation around the origin of a complex plane. The temporal delay between a force and a reaction becomes a spatial angle. We calculate the lag as a fixed rotation between two vectors. This single rotating arrow is the foundational building block for analyzing a car suspension to a continental power grid. Frequency domain mapping operates on a specific rule. Each time derivative drops a factor of in omega into the mathematical coefficient. Geometrically, multiplying by the imaginary unit I translates to rotating a vector by exactly 90 degrees on the complex plane. We can map the physical forces directly onto this compass. The restoring force of the material, its static stiffness, stands at the baseline phase, pointing to the right at 0 degrees. Velocity introduces one time derivative, dropping one in omega term. This shifts the damping force 90 degrees ahead of displacement, pointing straight up along the imaginary axis. Acceleration requires two time derivatives, introducing an I squared. This results in a negative sign, rotating the inertia vector a full 180 degrees, so it directly opposes the stiffness vector. The physical forces tearing at a vibrating structure are three static arrows fighting a tug-of-war on a geometric compass. This bracketed expression is the master equation governing that tug-of-war, the structural impedance. It explicitly groups the real terms, where inertia acts in opposition to stiffness, against the imaginary term representing the system's damping. At low frequencies, known as the quasi-static regime, the driving force only fights the baseline static stiffness. This keeps the phase delay near 0 degrees. At high frequencies, the mass-controlled regime causes the inertia term to overwhelm everything. This pushes the phase delay to 180 degrees, meaning the mass moves completely opposite to the direction of the force. As frequency increases, we reach a precise point where the 180-degree inertia vector perfectly matches and cancels the 0-degree stiffness vector. This is resonance. Because inertia and stiffness have annihilated each other, the driving force no longer fights the material's mass or rigidity. It only fights the 90-degree damping term. Structural resonance occurs at the point of total phase cancellation between mass and material stiffness. Without restoring forces, only damping limits the vibration. We can scale the problem to a coupled system, two distinct masses tethered to fixed walls, connected to each other by a central coupling spring. While the physical rules are identical, energy no longer stays in a localized loop. It cycles back and forth between the two components, creating a beating phenomenon as the energy transfers. Tracking this interaction requires upgrading the math into an eigenvalue matrix problem. This mass matrix tensor separates the inertia, mapping it across the coordinates for both distinct masses. In the stiffness matrix, the diagonal elements represent the isolated stiffness. The off-diagonal terms represent the physical coupling spring, dictating how motion in mass 1 leaks a restoring force into mass 2. This matrix acts as a structural ledger, tracking how multiple phases and forces interact simultaneously across a networked system. In a coupled matrix, phase defines the internal alignment of the masses. This architectural relationship between components determines the motion of the entire assembly. These internal relationships define normal modes. In the symmetric mode, the masses move with a phase difference of 0 degrees, vibrating perfectly in unison. Because they move together, the central coupling spring does not stretch or compress. It provides 0 resistance, causing the system to behave like a single mass with a lower resonant frequency. In the antisymmetric mode, the phase difference flips to 180 degrees. The masses move in direct opposition. Moving toward and away from each other maximizes the deformation of the central spring. This adds severe stiffness to the system and drives the resonant frequency drastically higher. Internal phase alignment literally rewires the effective physical stiffness of a multi-part structure in real time. Comparing the isolated oscillator to the coupled matrix clarifies this transition. While a single mast has one resonance peak, coupling splits it into multiple frequencies. This eigenvalue matrix math dictates the behavior of the largest physical structures in the modern world. Today, electrical engineers use these exact symmetric and antisymmetric mathematical modes to analyze and protect massive parallel three-phase electrical transmission lines. Mutual inductance and capacitive coupling between these massive wires act like a mechanical coupling spring. This splits power surges and traveling waves into different phase velocities. By understanding how to rotate a single imaginary vector by 90 degrees, engineers unlock the master key to stabilizing the resonant behaviors of the world's most complex networked grids.